A while back, I saw images like this. And the person posting them got them straight from the satellite. They didn't go online, they did not download these. They were actually receiving these images straight from the satellite sending them. I did some research and figured out I could build my own antenna using some old parts I collected and some parts I got online for relatively cheap. This video is how I built it. Let's dig in. So this is the satellite dish. It's a Unify Air Max point-to-point Wi-Fi dish. And after sitting in storage for a little while, this thing was dirty. It had a thick coating of dust on it, so I decided to clean it off real quick. At this point, I wasn't really sure how I was going to mount it, but I decided to remove the brackets anyways, just so while I was working on this, it wasn't jingling around. Because this has to be at such a high elevation, or rather pointed basically straight up into the sky from my location, mounting it on a pole that is vertical wouldn't really be ideal, but I did figure out a solution for this later on. The active element that was there, the Wi-Fi antenna, was relatively easy to remove. There was just a couple tabs holding it in place. Once I got it loose, I was able to remove the back end and slide the entire piece through. Then I was left with this odd looking hole. I needed to find a way to mount this PVC pipe to the dish and keep it center. So I decided to try my hand at 3D printing a custom bracket. I grabbed my calipers and took a bunch of measurements and put all of that into Autodesk Fusion. I am by no means a pro at this. I'm actually fairly new at it, but I was able to get a working bracket after 3 iterations. I bolted that into the satellite dish, and that gave me a really solid connection for my PVC pipe. The parts that I got online were the Newelec Sawbird GOES-LNA, or low noise amplifier, and the green antenna is the WA5VJB log periodic antenna. It is intended for 1.35 gigahertz all the way up to 9.5 gigahertz, but for GOES reception, you really only want 1.6, but that's where the Sawbird comes in because it really singles out that frequency. I then cut slits into the PVC pipe so that I could fit the antenna straight into the slit. It's pretty low tech, there's nothing fancy about it, but it does the trick. I did need a way to feed the coax cable through the PVC pipe without cutting any external holes into the 3D printed piece. So I just cut a small slit into the PVC pipe that I did eventually end up extending because it didn't quite fit right. Once I made sure the antenna fit, I fit my LNA right onto the antenna. The reason for this is because if you add the LNA after like a feed line or anything like that, you could actually introduce a lot of noise. So you connect it straight to the antenna and you mitigate that. I fed the coax cable through the slit that I created, and then I tightened everything down with some zip ties. This really is pretty low tech. If I were to make this more permanent, then I'd probably try to 3D print some kind of mount that would both weatherproof and really solidify this whole build. But the nice thing is I'm able to pull the insert out whenever I want. After that, it was really just assembling everything. Now, a key note is the active part of the antenna for the 1.6 gigahertz is actually the widest part of that green antenna, which means that that part has to be at the exact focal point where the parabolic shape of the dish focuses all of the refracted radio waves, which means that it actually has to be pretty low, and even in that image, it was a little bit high. I grabbed my RTL SDR, plugged it into my laptop just to make sure that everything was functioning correctly. Ran a few tests, and I was ready to take it outside and see if I could capture some images.
All right, so you can't tell,
It is extremely windy out right now, but I want to test this today, if possible. So we're gonna do it. All right, so I've got my antenna fed to my SDR, and first we need to figure out the angle. So I've taken a couple notes. Hello, it's like a bell. Taken some notes on the elevation and the azimuth of the antenna, or excuse me, the satellite. Object, azimuth. That's not the case for where I'm at. The wind was definitely a little bit much on my microphone, but I was basically just trying to line up the satellite using my iPhone compass. And then I actually used the ruler on my iPhone to calculate the elevation that the satellite dish needed to be at. So I will say the first time and even the second time and the third time did not really go according to plan. I was able to see something, but it wasn't really the signal that I was looking for. Come to find out, the antenna was sitting a little bit too high in the dish, which was, you know, not giving me enough of a signal or enough bandwidth to get the images. But the following day I did fix that, and I will show you that here. 5, 4, take 4. I think this is right. So this is the active element. Getting it in and putting it out. We've got it running. Whoa, this cable's heavy. Orientation matters a lot. Ooh, here we go. Okay. You got something? Orientation was wrong. There we go. All right, double sync. Let's go. That is a weak signal, but I don't know if I can boost it any. A full sync. I'm honestly not really sure how long this takes, so we're just gonna let it sit. Guys, we have something. Oh, don't throw errors on me, come on. This is so cool. We have a full planetary image. Gosh, this is wild. Just pointing a dish at a satellite 22,000 miles away. At this point, I was pretty excited just to be getting these images from the satellite. I did really want to capture an image without any of those banding, so I went back out a few days later and I got this. This has been such a fun project. I hope you have enjoyed watching the video. If you have any questions, leave them in the comments, and thanks for watching.